Hello everyone, I am Sumita and welcome to this deep learning project tutorial. In this video, we are going to build an image caption generator using Flickr8k Dataset. Personally, this was my very first AI project during my bachelor's degree. At that time, I had no knowledge about model architectures, datasets, model training, hyperparameter tuning, evaluation matrices, and many other fundamental concepts. I also did not have anyone to guide me on what I should learn first or which step I should follow while building an AI project. That's exactly why I am creating this tutorial. Through this video, I will try to explain every important concept in a simple and beginner-friendly way. So, even if you are starting from scratch, you will be able to follow along. Before starting any project, you should always understand its objective. The objective of this project is to build an image caption generator in Nepali language. There are plenty of tutorials and GitHub repositories available for English image captioning, but only a few research work have been conducted for Nepali image captioning. The good news is that the overall workflow is almost same as English image captioning, with only the dataset and language being different. By the end of this project, we will have a model that can generate a Nepali caption for a given input image. Before writing any code, let's first understand the dataset. Here is the one sample of dataset. You can see that image is paired with 5 different captions. So like that, each image is paired with 5 different captions. So let's briefly understand the architecture we will build. We will use a CNN, convolutional neural network, as the image encoder to extract visual features from the images, and an LSTM, that is long short-term memory network, as the decoder to generate captions word by word. I also want you to show one research paper. So go to the Google Scholar and search comparative analysis of image captioning. And then you will see here, let's scroll down. So here you can see the block diagram that we are also using same block diagram for this project. So you can have a look on this paper also. Now, without further delay, let's begin the project. I am using Kaggle notebook, but you can also use Google Colab or Jupyter notebook. Let's start by importing all the required libraries. So first we will import some Python libraries. Import OS, which help us work with different files and directories. Next we will import Pickle, which we will use it to save the image features after feature extraction. And next is NumPy, which is one of the most commonly used libraries for numerical operation in machine learning. And then import TQDM. This helps to display progress bar and makes it easy to monitor how much of the task has been completed and how much is still remaining. Now we will import TensorFlow and Keras module. So we will import VGG16 from TensorFlow.Keras applications from pretend CNN model will be used to extract meaningful visual feature from each image. Along with that, preprocess input, which preprocess the image in the format expected by VGG16 model. And you will notice that I am importing everything from TensorFlow.Keras instead of directly from Keras. In recent version, importing directly from Keras sometimes causes compatibility issues, so using TensorFlow.Keras is generally more suitable. Next we will import load image and image to array that help us to load image and convert them into array before feeding them into the CNN. For text preprocessing, import tokenizer. It converts word into numerical IDs that our neural network can understand. Next one is paired sequences. Since captions have different length, this function pairs shorter caption with zeros so that every input sequence has the same length. Neural network require input with consistent dimension. Next, we will import the model class, which we will use later while building our image feature extraction model. From TensorFlow.Keras.utils, we will import two categorical and plot model. Two categorical converts output word into one hot encoded vector during training, while plot model generate visual diagrams. Finally, we will import the layer required to build our caption generation model, that is input, dense, LSTM, embedding, dropout and add. Now that's all the required library have been imported successfully. The next step is to define the project directory. Instead of manually downloading the dataset from Kaggle and uploading it into your notebook, we can use the Kaggle Hub library to directly download the dataset. First import Kaggle Hub, then next use dataset download. Now in your browser search for Flickr8k Nepali dataset. Here you can see it, and now click this and open. You should copy this and paste here. Now when you run this command, Kaggle Hub automatically download the dataset and stores it into your notebook environment. Base directory, which points to the location of our Flickr8k dataset in Kaggle. Next one is working directory, where we will save generated files such as extracted image features and trained model during the project. Using variables for this directory makes the code cleaner and easier to manage throughout the notebook. Now we are going to extract features from the images. For feature extraction, we will use the VGG16 model, which is a pre-trained convolutional neural network that has already been trained on the ImageNet dataset, so it has learned to recognize a wide variety of visual patterns and objects. Instead of training a CNN from scratch, we can take the advantage of these learned features, which save both time and computational resources. Here, although I am using VGG16 in this tutorial, you are not limited to it. You can also use other pre-trained models such as ResNet, DenseNet, EfficientNet, Inception v3 or many others. We can see in the code that we have done model.layers -2.output. Why we have done that? VGG16 is designed to classify image, and our goal is not image classification. So we are removing that last two layer, and by removing we are only using the features learned by the network. Now let's extract the feature from the images in our dataset. We will first create an empty dictionary called features, which helps to store the extracted feature for every image. The key of the dictionary will be the image ID, and the value will be corresponding feature vector generated by VGG16. Next, we will specify the directory that contain all the images using os.path.join. Now, we will iterate through every image in the directory using a for loop. I am also using TQDM to display a progress bar. For each image, we will first create its complete file path. Next, we will load the image using load image. Since VGG16 expects an input size of 224 times 224 pixels, we will resize every image to it. After loading the image, we will convert it into NumPy array using image to array. Next step is to reshape the image. Currently, the shape of our image is 224, 2243, where the last dimension represents RGB color channels. However, VGG16 expects the input in the form of batch size, height, width channels. Since we are processing one image at a time, so we will reshape it into 1, 224, 224, 3. Here 1 represents the batch size. Next, we will pre-process the image using preprocess input. This function prepares the image exactly as VGG16 expectation. And this step is important because it helps the model to produce accurate feature representation. Now we are ready to extract the image features. We will pass the pre-processed image to model.predict. I have also set purpose is equals to 0, so TensorFlow don't print unnecessary progress message while processing thousands of images. The output of this prediction is feature vector that captures the important visual information from the image. Instead of storing the entire image, we will store only this compact feature representation. Finally, we will extract the image ID from the file name. We will repeat this process for every time in the dataset until all image feature has been extracted and stored. Here comma is missing. Okay, now let's debug the error. And also it is not taking this directory, so let's copy the base directory and directly paste it here. Oh, here is also a small error, that is not a comma. Finally, feature extraction is started. It will take some time to extract feature, so let's continue with the code. Once you have extracted the features, you definitely don't want to repeat this entire process every time when you run your notebook. Feature extraction is one of the most time consuming steps, so it is a good idea to save the extracted features to a file. We will use Python's Pickle module for that. Here I am using Pickle the dump to save the features dictionary. I will specify the file path using os.path.join and save it as imagefeatures.pkl inside the working directory. Notice that I am opening the file in a write binary mode because Pickle stores data in a binary format. Once this is done, all of our extracted feature will be safely stored in a single file. Later, whenever we need this feature again, we can simply load them instead of extracting them from scratch. To do that, we will open the same file in read binary mode, RB mode, and use pickle.load. This will reload the entire feature dictionary in just a few seconds, which saves a huge amount of time. I highly recommend doing this in your deep learning project whenever you have expensive preprocessing or feature extraction steps. It makes experimentation much faster because you don't have to repeat the same computation every time. Now let's load the captions. We will open the captions.txt file using open function along with os.path.join. Use the base directory because that is where our caption file is stored. We will open the file in read mode. You will also notice that I am calling next f before reading the file. The reason for this is that the first line of the file is just a header and contains something like image caption. Since we don't need the header, next f simply skips the first line, allowing us to read only the actual caption data. After that, we will read the entire file using f.read and store it in the caption docs variable. Now that we have loaded the captions, we will create a mapping between each image and its corresponding captions, just like we did for the image features. I will start by initializing an empty dictionary called mapping. Since each line in the caption file contains an image file name followed by its caption, we will iterate through the file line by line using tqdm captions docs split, so we can keep track of the progress. For each line, we will split it by spaces to separate the image name from the caption word. Before moving ahead, we will check whether the line is valid. If it has fewer than 2 characters, we will skip it. This helps us avoid any empty lines. Next, we will separate the image file name and the caption tokens. The first token is the image ID and everything after that belongs to the caption. We will remove the file extension from the image name by splitting it at the period and keeping only the first part. Then, we will join the remaining caption tokens back into a complete sentence. Since each image can have multiple captions, we will first create an empty list for that image ID if it does not already exist in the dictionary. Finally, we will append the caption to the list for that image. Once the loop is complete, we will print the total number of images in the mapping and also display the first 5 captions for a sample image so we can verify that everything has been loaded correctly. Once the loop is complete, we will print the total number of images in the mapping and also display the first 5 captions for a sample image so that we can verify everything has been loaded correctly. The image file name still contains .jpg extension, But we don't need that because we have already been using image IDs without extensions throughout the project. So I will remove the extension by splitting the file name at the period dot and keeping only the first part. As you see, it finishes very quickly. If we check the length of the mapping dictionary, you will see that we have mappings for all the images, which means everything has been loaded correctly. Now, the next step is to pre-process the caption. To keep the code organized, I will create a separate function called clean. This function takes the mapping dictionary as input, process every caption one by one. We will iterate through each image ID and its corresponding list of caption. We will add two special tokens to every caption. At the beginning, we will add the start token, and at the end, we will add end token. These tokens helps the model understand where a sentence starts and where it ends. During inference, once the model predicts the end sequence token, we will know that it has finished generating the caption. Now let's see the difference. Every caption now begins with the start sequence token and ends with the end sequence token. This clean text is much easier for our caption generation model to learn from. Now that we have finished pre-processing the captions, the next step is to collect all of them into a single list. I will create an empty list called all captions, then I will iterate through each image ID in our mapping dictionaries. Remember, every image has multiple captions, so for each image, I will loop through its list of captions and simply append each one to all captions. By the end of these loops, this list will contain every caption in the entire dataset. Let's print the total number of captions. As you see that we have around 40,454 captions. That's exactly what we expected because Flickr8k Dataset contains approximately 8,091 images. And each image has 5 different captions. If we display the first few captions, you will see that they are already pre-processed. They contain start sequence and end sequence tokens and are ready for the next stage. Now that we have all the captions in one place, we need to convert this text into number because deep learning model can't understand raw text. For that, we will use Keras Tokenizer. I will first initialize the tokenizer. Then I will call fit on text and pass all the captions. During these steps, the tokenizer scans through every caption in the datasets, identifies all the unique words, and assign a unique integer ID to each word. For example, one word might get ID 1 and another word might get ID 2 and so on. This creates the vocabulary that our model will use during training. Once the tokenizer has processed all the captions, we will calculate the vocabulary size. I will simply take the length of tokenizer dot word index and add 1. We add 1 because Keras reverses index 0 for padding, which will be useful later when we make all caption sequences the same length. Let's print the vocabulary size. This tells us how many unique words are present in our dataset, and our model will learn to predict one of these words at every time step while generating captions. Next, we need to determine the maximum caption length. Different captions have different number of words. Some captions are very short while others are much longer. However, neural network expect input to have the same length. So, we will calculate the length of every caption by splitting it into words and then find the maximum value. This gives us the longest caption in the dataset. We will store that value in the max length variable. Later, we will use this value to pad all shorter captions so that every sequence has exactly the same length before feeding them into the model. Let's print the maximum caption length. Now that we know the vocabulary size and maximum sequence length, we are ready to prepare our dataset for training. The next step is to split the dataset into training, testing and validation set. First, I will import Python's random module. Then I will set a fixed random seed. Using a fixed seeds ensure that every time we run this notebook, we get exactly the same data split. This makes our experiment reproducible. Next, I will extract all the image ID from the mapping dictionary, then randomly shuffle them. Shuffling is important because we don't want the image to remain in their original order. A random distribution helps create a fair training, testing and validation set. Now, we will divide the data set. We will use 80% of the image for training, 10% for testing and remaining 10% for validation. First, we will calculate the index corresponding to 80% of the dataset. Then we will calculate the index for the next 10%. Using this index, we will slice the stuffed list of image IDs. The first 80% will become our training set, the next 10% will become our testing set, and the remaining image will be used as the validation set. Finally, let's print the number of images in each split. As you can see, the dataset has now been divided into training, testing and validation set. Using separate dataset is very important. The training set is used to teach the model, where the validation set helps us monitor the model's performance during training and tuning hyperparameters. Finally, the test set is used only after training is complete to evaluate how well the model perform on completely unseen images. We have 6,472 images for training, 809 for testing and 810 for validation. Now that our data preparation is complete, we are ready to build the data generator that will feed image features and caption sequences into our neural network for training. You might be wondering why we need a data generator instead of simply loading everything into memory. The reason is memory uses. For a small dataset, you could load everything at once, but for larger datasets, this quickly consumes a lot of RAM. If your system does not have enough memory, your notebook or collaboration may even crash. A data generator solves this problem by loading only a small batch of data at a time. Once the model finishes training on that batch, the generator loads the next batch. This makes training much more memory efficient. So, let's create a function called data generator. This function takes several inputs, including the image IDs, the caption mapping, the extracted image features, tokenizers, maximum caption length, vocabulary size, and the batch size. Inside the function, you will notice a while true loop. This creates an infinite generator that continuously produces batches of data whenever the model requests them during training. Next, I will initialize three empty lists, x1, x2 and y. x1 will store the image feature vectors, x2 will store the input text sequences, and y will store the target word that model should predict. We will also initialize a counter called n to keep track of how many images have been processed in the current batch. Now, we will iterate through every image ID in our training set. For each image, we will retrieve all its captions from the mapping dictionary. Then, we will process each caption one by one. The first thing we will do is to convert the caption into a sequence of integer using tokenizer.text to sequence. Instead of working with words, we now have a sequence of tokens ID. For example, a caption like केटी काठको घरभित्र जाँदैछ might become something like 1, 54, 132, 87, 412, 903, 2. Now comes one of the most important part of image captioning. Instead of giving the entire caption to the model at once, we will create multiple training samples from a single caption. Again, for example, suppose our caption is केटी घरतिर जाँदैछ. Our training pair look like input at first it start sequence and then in target KT. Then the next training sample will became like for example for input start sequence and then KT. And what will be the target? Target will be जाँदैछ. Then next input will be start sequence KT जाँदै and then target will be भित्र. And then process continues until the model finally learns to predict the in sequence token. In other words, the model learns to predict one word at a time using both the image features and the word it has already seen. This is exactly how caption generation works during inference as well. Next, we will pad every input sequence using pad sequence. Since captions have different length, padding ensures that every sequence has the same size, which is required for neural network. We will pad each sequence to the maximum length that we calculated earlier. For the output word, we will apply toCategorical function. This converts the target word into a one-hot encoded vector. For example, if our vocabulary contains 8000 words, the output becomes a vector of length 8000, where only the correct word has the value 1 and every other position is 0. Now, we will store everything. The image feature vector goes into x1, the padded caption sequence goes into x2, and the one-hot encoded target word goes into y. We will repeat this process for every caption of every image. Once we have processed the specified number of images equals to the batch size, we will convert all three lists into NumPy arrays. Finally, we will use the yield statement. Unlike return, which stops the function, yield returns one batch to the model and then pauses the generator. When the model needs another batch, the generator simply resumes from where it left off. This is what makes generators so memory efficient, and that's why they are commonly used in deep learning. Now that our data generator is ready, let's build the image captioning model. We will use an encoder and decoder architecture. The encoder has two branches. The first branch processes the image features extracted from VGG16. The second branch processes the caption sequence. Let's start with the image branch. We will define an input layer with a shape of 496 because that is the size of feature vector produced by VGG16. And if you are using another model like ResNet, EfficientNet, then please check the shape and then use it. Next, we will apply a dropout layer, so a dropout of 0.4. Dropout randomly disables some neuron during training, which helps reduce overfitting and improves the model ability to generalize. After that, we will use a dense layer with 256 neuron and the radio activation function. This compresses the original 496-dimensional feature vector into a more compact representation while learning more meaningful image features. Now let's move to the next branch. The input here is a caption sequence with a length equal to max length. The first layer is embedding layer. The embedding layer converts every word index into a dense 256-dimensional vector. Instead of representing words as a simple integer, embeddings allow the model to learn meaningful relationship between words. You will also notice max 0 is equals to true. This tells the models to ignore the padding tokens that we added earlier. After the embedding layer, we will again drop out to reduce overfitting. Then, we will pass the sequence through an LSTM layer with 256 units. The LSTM learns the context of sentence and produces a feature vector representing everything the model has read so far. At this point, we have two feature vectors. One represents the image, the another represents caption sequence. Now, we need to combine them. We will use add layer to merge between feature vectors. This creates a joint representation that contains information from both image and the caption. Next, we will pass the combined representation through another dense layer called ReLU activation. Finally, we will use a dense layer with a softmax activation. The number of neurons in this layer is equal to our vocabulary size. The softmax layer outputs a probability for every word in the vocabulary, and the word with the highest probability becomes the model's predicted next word. Now, we will create the complete model using model class. The model has two inputs, the image features and the caption sequence. And it produces a single output, that is the probability distribution over the vocabulary. Finally, we will combine the model. We will use categorical cross entropy as the loss function because predicting the next word is a multi-class classification problem. For optimization, we will use Adam Optimizer, which is one of the most widely used optimizer in deep learning. We will also monitor the training accuracy during the learning process. Before moving on the training, let's visualize the architecture using plot model. This gives us a clear diagram showing how the image branch and text branch merge together before producing the final caption prediction. Okay, let's run it. Here I encounter an error. The spelling of activation is mistake while typing, so correct it. Okay, again error. Oh, here also. Let's correct here also. Now you can see a full model ready for training. Here you can see layer by layer. Okay, you can analyze by yourself. I think you will understand it. Now that our model is completely built, we are finally ready to train it using the data generator we created earlier. Let's import matplotlib. For visualization, it is extremely useful for visualizing the training process. Later, we will use it again to plot graphs showing how the loss and accuracy changes over time. Next, I will define two hyperparameters, that is epochs and batch size. I will set the number of epochs to 20. Okay, what is an epoch? An epoch means one complete pass through the entire training dataset. For example, if our training dataset contains 6400 images, then during one epoch, the model will see every one of those images exactly one time. After completing the first epoch, the model does not stop learning. Instead, it starts another epoch and goes through the same dataset again and again. With each epoch, the model gradually updates its weights and usually becomes better at predicting captions. Of course, training too many epochs can sometimes lead to overfitting, where the model memorizes the training data instead of learning to generalize. That's why we will also monitor the validation performance during training. Next, I will set the batch size to 32. Instead of feeding all the training samples to the model at once, we will divide them into smaller groups called batches. Here, each batch contains 32 images. The model processes one batch, calculates the error, updates its weights, and then moves to the next batch. Using batches makes training much more memory efficient and results in more stable optimization. Now let's calculate the number of training steps. You will notice I am using steps equals length of training dataset floor divided by batch size. This tells Keras how many batches it should process during one epoch. For example, if we have 6400 training images and the batch size is 32, then one epoch consists of approximately 200 training steps. Each step corresponds to processing one batch generated by our data generator. Similarly, we will calculate the number of validation steps. These determine how many validation batches are evaluated after every training epoch. Now, we will create our generator. First is train generator. This generator continuously loads batches from the training dataset. The second one is val generator, which does exactly the same thing for the validation dataset. Remember that our generator does not load the entire dataset into memory. Instead, every time the model requests a new batch, the generator prepares that batch on demand by loading the image features, converting caption into sequences, padding them, and creating the target outputs. This makes training possible even on a system with limited RAM. Now comes the most important line of the entire training process, that is model.fit. This is the function that actually trains the neural network. Let's understand what happens internally when we call model.fit. At the beginning of every epoch, Keras asks the training generator for the first batch. The generator returns three things: the image features, the input caption sequence, and the target words. This becomes the input and outputs for the model. The model then performs a forward pass. During the forward pass, the image features travel through the image branch and the caption passes through the embedding and LSTM branch. Both branches are combined, and finally the softmax layer predicts the probability of every word in the vocabulary. For example, suppose the correct word is KT. The model might predict the probabilities like KT equals to 0.72, and then for Biralo 0.10, and for Keta 0.05, and very small probabilities for the remaining other vocabulary, other words. Next, Keras compares this prediction with the actual target words. Since our target is 1 encoded, only the correct word has the value of 1, while every other word has the value of 0. To measure how different the prediction is from the true answer, Keras compute the categorical cross entropy loss. The cross entropy loss becomes small when the model assigns a high probability to the correct word. If the model predicts the wrong word with high confidence, the loss becomes large. So, you can think of the loss as a measure of how wrong the model prediction is. Once the loss has been calculated, Keras Keras perform backpropagation. During backpropagation, the gradient of the loss with respect to every trainable parameter are computed. These gradients tell the model how each weight should change in order to reduce the prediction error. Finally, the ADAM optimizer updates all the weights of the model. ADAM automatically adjusts the learning rate during training, which usually helps the model converge faster than traditional gradient descent. After updating the weights, the model requests the next branch from the generator. This process repeats batch after batch until all the training steps from the current epoch have been completed. Once an epoch finishes, Keras evaluates the model on the validation generator. I think you have noticed that the validation data is not used to update the model weights. Instead, it simply measures how well the model performs on the data it hasn't seen during training. This gives us a better estimate of how well the model is likely to perform on completely new images. All the information generated during training is stored in the history object. This object contains values such as training loss, training accuracy, validation accuracy for each and every epoch. We will use this value in the next step to visualize the learning process. Both the training loss and the validation loss should gradually decrease. Similarly, the training and validation accuracy should improve over time. If the training accuracy keeps increasing while the validation accuracy stops improving or starts decreasing, that is often a sign that the model is beginning to overfit. By analyzing this graph, we can decide whether to train for more epochs, stop training early, or adjust some of the model hyperparameters. Once the training is complete, our model has learned relationship between image features and caption sequences, and it is ready to generate the captions for completely unseen images. Depending on your hardware, training process will take some time, from several minutes to few hours. If you are using a GPU, training will be much faster than using only a CPU. Once the training is completed, we will save the trained model using model.save. This saves the complete model including its learned weight so that we don't have to retrain it again and again in future. Now let's plot graphs. The first graph shows the training loss and validation loss. Ideally, both curves should decrease as training progresses. A decreasing loss indicates that the model is learning meaningful patterns from the dataset. The second graph shows the training accuracy and the validation accuracy. As training continues, we would like both accuracy to increase. If the training accuracy keeps increasing while the validation accuracy stops increasing or starts decreasing, it may indicate that the model is beginning to overfit the training data. These plots give us a quick way to understand whether our model is learning properly or not. Now that our model has been trained, the next step is to generate captions for new image. To do that, we will first create a smaller helper function called idx to word. Remember that our model does not predict word directly. Instead, it predicts an integer representing a word in our vocabulary. This function simply converts that predicted integer back into its corresponding word using the tokenizer. Now, let's create the main caption generation function called PredictCaption. This function takes 4 inputs: the trained model, the extracted feature vector, the tokenizer, the maximum caption length. The generation process always begins with the special token, that is start sequence. This tells the model that it is starting a new caption. Next, we will enter a loop that runs until we either reach the maximum caption length or predict the end sequence token. Inside the loop, we will convert the current sentence into a sequence of integers using tokenizer the text to sequence. Then we will pad the sequence using pad sequences so that its length matches the maximum sequence length expected by the model. Now, we will pass both input to the model. The first input is the image vector extracted from VGG16, and this process continues one word at a time until the model predicts the special token, that is in sequence. Finally, the function returns the complete generated caption. Now, it's the time to evaluate how our model performs. So one of the most common evaluation metrics for image captioning is BLEU score. BLEU score stands for Bilingual Evaluation Under Study. BLEU score compares the generated caption with the human written reference caption. The closer the generated caption to the actual caption, the higher the BLEU score. First, we will create two empty sets called actual and predicted. Then we will iterate through every image in the test dataset. For each image, we will retrieve the ground truth caption from the mapping dictionary. Then we will generate a caption using our predict caption function. The reference captions are split into individual words and stored in the actual list. Similarly, the generated caption is also split into words and stored in the predicted list. After processing all the test images, we will calculate the BLEU score. Here, I am calculating BLEU1 and BLEU2. BLEU1 measures the overlap of individual words, also known as unigrams, and BLEU2 measures the overlap of two consecutive words or bigram. Generally, higher BLEU score indicate better caption quality. You can also calculate BLEU3 and BLEU4. And there are also other several matrices like meter, log, and many more. BLEU is one of the most widely used evaluation matrices for image captioning system. Here I am also writing the code for calculating BLEU3 and 4. But I am uncommenting it because it takes lots of time to calculate the score. So for now I am only calculating BLEU1 and 2 only. But if you want to check, then you can calculate all BLEU from 1 to 4. Okay, finally, let's test our model on an actual image. I will create another function called generate caption. This function takes an image file name as input. First, it will load the image from the dataset. Then it retrieves all the human written caption associated with that image. These are the ground truth caption that we will use for comparison. Next, we will call predict caption to generate a caption from the same image. Finally, we will display both the actual captions and the predicted caption along with the image itself. This gives us quantitative evaluation of our model. Instead of looking only at numerical metrics like BLEU score, we can actually see whether the generated caption accurately describes the image. Let's run the function with one of the test images. Okay, let's wait for some time until BLEU score calculation gets completed. As you can see, the model generates a caption that captures the main objects and activities in the image. It may not be identical to the human written caption, but if it correctly describes the scene, that is a good indication that our captioning model has learned meaningful visual and textual relationship. And that's it. We have successfully built an end-to-end image captioning system. We started by extracting image features using VGG16, processed the captions, built a vocabulary, created a custom data generator, designed an encoder-decoder model with LSTM, trained the model, evaluated it using BLEU scores, and finally generated captions for completely unseen images. I hope this tutorial helped you understand not just the code but also the concept behind it. If you found this video helpful, Don't forget to like the video and subscribe to the channel for more tutorials on deep learning, computer vision and natural language processing. Thanks for watching and I will see you in the next video.